Okay, review time of a function signal generator. In fact, the cheapest function signal generator I could find on eBay. It is so generic there's no manufacturer of the part. It just seems to have this generic text on it, GDS function generator, a date, and version 2.1. Let's just overview what's on the board before we turn it on. There's a power jack. It seems to accept between 7 and 9 volts. Now the one I bought didn't seem to come with a wall wart, so I'm powering it up externally with a loud power supply. That's at least a couple wires are about. It's got a power button, an amplitude adjust, an offset, a direct digital synthesis output, and then a what they call high-speed output, which is basically just a GPIO. So when you're generating high-speed square waves, it just bypasses the analog section of the board. Okay, powered on. Obviously my oscilloscope showing a waveform. It's in the sine mode, and it's producing a 3,900 hertz frequency. Very typical for, say, audio work, if you're trying to trace an amplifier and trying to inject a signal into it. The amplitude adjust, of course, adjusts the size of the waveform. You can see it clips as it gets to the edge of its excursion rate, and there's a offset as well. You can see this behavior where it will clip, of course, and that's fine. So just running through all the functions, there's a noise function, the high speed function, which is a square wave output, the sine, the square wave, the triangle wave, the sawtooth wave, the reverse sawtooth, ECG. Kind of like a heartbeat, I guess, more of a novelty waveform, not really as much use that I can imagine in electronics design. In terms of actually adjusting the output frequency, you have to select the frequency step, then come back to the waveform that you desire. You can then adjust the frequency, and then you just press start to run. And then once it's running, because it's a little tiny microprocessor thrashing away, you can't adjust the frequency. You have to stop it again, change the frequency, and then start running again. Very, very clunky interface. This is the noise waveform. It has this sort of behavior here. It varies basically its amplitude. So the second output is what they call the high-speed output. You can see there's an 8 MHz on the display here, and an 8 MHz square wave. Just like the other direct digital synthesis mode, you actually have to stop the generator before you can change it to another frequency. It's kind of a curious selection of frequencies. It's just a binary stepping of a 1, 2, 4, or 8 megahertz. So I guess useful if you want a sort of a moderate speed clock into some digital circuitry you might be prototyping. Okay, let's look at some of the design flaws of this module. I got it in a sawtooth mode, obviously, and it looks fine. But when you zoom into it, you can sort of see some of the fundamental errors. There's what appears to be a almost like a sine wave imposed upon the waveform, and if you were to measure between these two peaks, you'd find it's exactly 1 megahertz, which is obviously one of the fundamental frequencies of the microprocessor. Essentially, they haven't, well, one or two things. They haven't isolated the digital ground from the processor adequately from the analog section. You can see that there's no plane management on the thing, nor do they have a decent filter on the output stage. So kind of a fundamental error you can make easily on a digital synthesized signal generator. So, and there you go, it's present here, of course, so beginner's error. Okay, I have my spectrum analyzer running here, and I've got the thing doing a 65 kilohertz sine wave, which is a high as frequency as it can generate. This is a really good demonstration of sort of the flaws where they don't understand what an anti-aliasing filter is, and they haven't filtered the output properly. Obviously, this very large peak up here is where the most energy is, of course, where the 60 kilohertz is. But you can see all this junk around here. I have my marker at 8 megahertz. No surprise that happens to be one of the frequencies the CPU is running at. You're getting a lot of leakage through from the digital section, and another peak at 7, another peak at probably 6 and 4. All this is so unnecessary, actually, and it's a well-described literature. Pick up any old Hewlett-Packard design function generator. You can take a look at the output sections there, and a real good way of understanding how you should actually do it. So, again, just demonstrating a design which doesn't have a great deal of sophistication. Okay, fractional synthesis. Here's one that's classically not done so well. Obviously, I got it set for about a 59 kilohertz square wave. And if you look at the output of the scope here, I got an infinite persistence mode, and of course you can see it's triggering on the rising edge, and the scope's showing, of course, all sorts of jitter on the output waveform, and again, just a real sign of weakness in the design. Okay, really straightforward topology. Here's a little tiny microprocessor that pop up the data sheet. Basically, it just thrashes away as hard as it can to create the waveforms. That's why the keyboard becomes non-responsive when it's generating. You see a lot of placements here. It's basically an R2R divider, so they're not using any sort of internal D-to-A converter. They're converting it with these resistors here. Again, pretty weak because obviously these components will have tolerances, and that will result in all sorts of strange artifacts. Crystal, of course, associated with the processor. Pop up the data sheet here. It's socketed. I have no idea why, but it's a voltage inverter, a capacitive voltage inverter. It runs fairly slow, and yes, there's no real great provisions to get the noise off of that being coupled into the system. A dual op amp here. You can see it's been soldered twice. That's basically because I blew up the original one. This thing can go like plus or minus 14 volt outputs, but when you run it to a 50 ohm input to a spectrum analyzer, you can really quickly overload the poor little op amp, and it blows out. Again, it's just an op amp driving out to the BNC. There's no decent push-pull stage on it. A little keyboard here, of course. The input, there's a 78LO5, so you feed this thing like 9 volts, and it gives you, like, of course, the 5 volts, which I'm sure goes to the processor. The back is completely unpopulated, other than the two potentiometers for the voltage control. So there you go, a very straightforward design, and all sorts of classic traps inside of it that you would commonly make, maybe at a university course or something, because I presume that's where this thing came from.